Vertical angles, really complicated definition, but what happens is you take two lines and you intersect them, and you get vertical angles. This set is a vertical set, so these two angles are vertical to each other, and this angle is vertical to this angle. So you have intersecting lines, you get two pair of vertical angles, opposite angles. Then you have congruent angles, so any two angles that have the same measure are congruent. Yeah, we haven't got there yet though, but yes, they are. That's okay. You're just ahead of us. Okay, so 40 degrees is congruent to 40 degrees. Or any measure of angle, as long as the other angle has the same measure, they're congruent. Complementary angles add up to 90 degrees. Now, the silly way that I have developed to remember this is that if somebody compliments you, they are right to remember 90 degrees. Okay, so any two angles that add up to 90 degrees will be complementary. So you can have them actually built together like this, where they make a 90-degree angle, or you can have two angles kind of off in space, and they can add up to make 90 degrees. And then supplementary angles add up to 180 degrees. And we can have that connected as well, where you have two angles that make a straight line. A straight line is 180 degrees. So these two angles add up to 180. Or you can have angles off in space that add up to 180. So if this one was 40, this one would be 140. Think of a duplex, right? Duplexes are two houses next to each other. They're adjacent. They share a wall. Adjacent angles are like that. They share a wall, so they touch. So if I have something like this, angle 1 is adjacent to angle 2. So they share a wall. And then you have a linear pair. Okay, whenever, there's two ways to have a linear pair. We can have like the same thing as vertical angles, where you get two intersecting lines, and that gives me 4 angles. And any two angles that make a straight line would be a linear pair. So in this picture, I'd have 1 and 2 make a linear pair, 2 and 3 make a linear pair, 3 and 4 make a linear pair, and 4 and 1 make a linear pair. So any two angles that can form one of the straight lines. Or you can have a line and a ray. So 5 and 6 are also a linear pair. Yeah. Yes. Yes. Adjacent angles can be complementary, supplementary, or they could also be a linear pair like this picture. Well, actually, these pictures too.
So what if you had a linear pair, like it was just like a straight X, so all the angles of it would be 90, and still be complementary?
Yeah, they would. Well, no, they would be supplementary, because if you had because you'd have 4 90 degrees, right?
Yeah.
So these two would add up to 180. So these would be supplementary, supplementary, supplementary. Yeah, they wouldn't be complementary in this case. Angle bisector is any ray that cuts an angle in half. So if I have just some angle out here, and I come in with another ray, and then this length and this length are the same, or not length, but angle measure. So maybe that's probably about a 20 and a 20. Cuts it in half. So sort of like a segment bisector, but it's bisecting an angle instead of a segment. One other thing. Linear pairs are all supplementary. But, okay, and this is important, not all supplementary angles are a linear pair. Okay, and the way this works, linear pairs are adjacent. They're touching. So they have to be connected together and make a straight line. Supplementary angles are just any two angles that add up to 180. So you can have like two angles floating off in space, nowhere near each other, and that can still be supplementary. But the linear pair has to be attached. Does that make sense? So they both add up to 180 because they're both supplementary, so they add up to 180. But with the linear pair, they're touching. With just, if it's just supplementary, they can be any two angles that add up to 180. Sort of like every square is a rectangle, but not every rectangle is a square. It's kind of the same idea. Every linear pair is supplementary, but not every supplementary pair is linear. Because linear means they have to be touching. They share a side. Okay, so there's postulates and then there's theorems. And remember, theorems were proven or need to be proven. In this case, these have been proven. And then postulates are accepted as true. The angle addition postulate is very similar to the segment addition postulate, which is if I have an angle, ABC. Yeah, you'll want these. Okay, so I have an angle ABC, and there's some point out here D that's inside the angle. So we have the interior of the angle, and then anything else over here is the exterior. Then if I take a line or ray, and I make a ray here to point D. Okay. I'm going to call this angle 1, and I'm going to call this angle 2. And I'm going to call the whole thing, well, I'll just keep it ABC. Okay. The measure of angle ABD, so that's angle 1. Oh, and that's what this little M out here means. That means the measure of the angle. Okay, so when we talk about, if you have this ABC, you're talking about the actual physical angle itself. If you have this ABC, you're talking about the degrees of the angle. So this is the actual angle. This is how many degrees the angle is. Okay, so we have the measure of angle 1 plus the measure of angle 2, that's DBC, is equal to the measure of the whole thing. So this is one of those things like if I take this angle and I cut it, then the two pieces equal the whole. Sort of like if you cut a piece of pizza and you take a slice of pizza and it's too big and you cut it, the two new pieces equal the one big piece. Does that make sense? Angle bisector postulate, any angle has exactly one bisector. So if I have an angle, and let's say this angle is 30 degrees, the whole thing, and I come in and I cut it, well then this part is 15 degrees and this part is 15 degrees, and there's only one line that will cut that angle perfectly in half. So there's only one angle bisector. And then two angles that form a linear pair are supplementary. Well, if I have two angles and they make a linear pair, this angle and this angle add up to 180. And that's because a straight line is 180 degrees. Okay, then we have the linear pair theorem. Well, the postulate says that the linear pair is supplementary. The linear pair theorem says that that means they add up to 180 degrees. So the linear pair theorem is just taking the postulate and making it a little more specific and giving it an actual number value. That's the only difference between those two. And then the vertical angle theorem, it says if two angles are vertical, then they are congruent. So if I come in and I make some vertical angles, label them. Angle 1 is going to be congruent to angle 3, and angle 2 is going to be congruent to angle 4. So the angles across from each other are the same size. Yeah.
Can you explain your drawing for drawing?
Yeah, so I had the big green angle, and it was 30. And then I draw the blue ray, the angle bisector, and it cuts the 30 in half and gives me 2/15.
Also, number 10, how would you solve that problem?
You can't solve this.
You don't? Okay.
Yeah, because we don't know what any of these measures are. Like if I knew the whole thing and one part, I could find the other part. Or if I knew the two parts, I could find the whole thing. But right now, I'm just saying that this piece plus this piece equals the whole big piece. I don't know any values. I can't solve it. I can't do anything with it. It's just there. Good? Okay. So finding a complement and a supplement. Complement is 90 degrees. Supplement is 180 degrees. So to find the complement and supplement, we just subtract. So the complement of 35 is 90 minus 35. The supplement of 35 is 180 minus 35. So 90 minus 35 is 55, and 180 minus 35 is 145. We can also have a compound statement with these. I can find the complement of the supplement, or I can find the supplement of the complement. If you see these, you do this first. And then you do this part second. Okay, so if I say to find the complement of the supplement of, let's say, 123 degrees. Okay, I'm going to find the supplement of 123 degrees first. So I'll do 180 minus 123, which is going to be 57. Then I find the complement of 57. So that'll be 90 minus 57, which is going to be 43 degrees. And that's my final answer. So I find the supplement. I do the second part first. And then I take the first part, the complement of that answer. Do you want to see another one? Okay. Just another example. If I wanted to find the supplement of the complement of 36. First I have to find this. So I have to do 90 minus 36, which is 54. Then I take supplement of 54 because I found this answer. So I do 180 minus 54, and that is 126. So that is the answer of the supplement of the complement. So you just find the second part first. But 126 and 36 don't equal 180. Right? So if I was going to, okay, so I would have this straight line here, right? And I would have the 90 degree part. And I would have the 36 is here. Well, that makes this 54. And then I have to find basically all of this over here to make the straight line with the 54. Is that a little better? Okay. Picture-wise, this is what I'd be finding over here.
So it's always, for the second one?
You do the second one first, And then whatever that answer is, then you do the first part using the answer from this part.
Yeah, do the compound statement. You see how the first sentence says the complement second and complement first?
Yeah, well, so it's the second, it's the part that says, so if I can do the complement of the supplement, I'll find the supplement first. Or if I do the supplement of the complement, I'll find the complement first. Yeah, so it's the second part first. Yeah. We can also have pictures like this where we need to find the missing angles. What we know is a straight line will add up to 180. So these two together will equal 180. We also know that vertical angles equal each other. Do you see that? So y and 123 are equal to each other, so that means y is going to equal 123. And then x adds up to 180, so x is going to be 180 minus 123. So that's 57, yeah. Good? And if you forgot the vertical angles, just like you forgot that they're vertical angles, you could do 123, the 180 minus 123 to get the 57 over here, and then you could use this straight line equals 180 and do 180 minus 57 and end up with 123. So there's two ways to get the answer. Just remembering vertical angles just makes it faster. You have to know the definitions, yeah. And you have to know that straight lines add up to 180. And you have to know that 90-degree angles add up to 90. That's really all we're using here. Okay. So let's look at this. We're going to find the complement of 56, the supplement of 93, and then the missing angles. Okay, so complements add up to, anybody remember? 90, yes. So I'm going to do 90 minus 56. So that's 34. And that means supplements add up to 180. So 180 minus 93, which is 90 minus 3, which is 87.
And let's just say the compound part would be there.
We could do find the supplement of the complement of, what number would you like?
Oh, I thought you based it off.
Oh yeah, no, I can make it. You want to do 56?
Yeah.
Okay. So first I'd find the complement of 56, which is 34.
Yeah.
And then I would do 180 minus 34.
Okay, so you just throw it out
Through this, yeah, I take the 180 from the supplement. I know this is 34 because of A. And so then I do 180 minus that, so that's 126. Okay, now here I have vertical angles because this line and this line give me a pair of vertical angles, but it doesn't help me in this situation because this angle is going to be the same as this whole thing here, but that doesn't tell me anything. So I'm not going to use the vertical angles on this one. Instead, I have this 90-degree angle. So I know that these two are going to add up to 90 degrees. So x is going to be 90 minus 43, which is going to be 47. So that tells me this is 47. And then to find y, I have a straight line. So I know this whole thing would be 180. So y would be 180 minus 43. So that would be 137. Does that make sense? So you look at the picture to see what you have. If vertical angles help, you can use vertical angles. If the 90-degree thing works, you can use the 90-degree thing. If the straight line part is what you need. Yeah, when you make an X. So we have one here too. Let me do my X. See my X? So this angle and this angle will be the same. Okay. that's important. I don't need it to find y, but I will probably need it to find x. And here's why. Y I can find using the 90 degrees. Right here. So that's going to be 54. So that's 54 right there. X has a vertical angle, but it's this vertical angle right here, so that doesn't help me. But if I look, these three angles together make this straight line. Do you see that? So these three angles together are going to add up to 180. So x is going to be 180 minus this 54 and minus this 27. So I'm going to cheat. So that's going to be 99 degrees. If we had to, we could find these other two missing angles as well using kind of the same ideas if you needed to. All right, a conditional statement is if-then. If you do this, then this will happen, kind of thing. If you study and do all your homework, then you'll get a good grade. If you go to work, then you'll get a paycheck. You know, conditional. There has to be a condition on the thing happening. A lot of, you know, in my household is if you do all your chores and your homework, then you can have dessert, kind of thing. So if then, P is the condition, Q is the result. The hypothesis is what's known as the if part. So if you have the sentence, if you clean your room, you can go to the pool. That's another one that happens in my house a lot. Okay. The hypothesis is the if you clean your room part. Oh, then he can go to the pool. The conclusion is you go to the pool. I guess the hypothesis doesn't actually have the if. So the hypothesis is the if part. It's the condition. It's the guess about what will happen. And then the conclusion is the then part. So if the hypothesis occurs, then the conclusion follows. If the hypothesis doesn't occur, then the conclusion goes away. A counterexample is any example that shows it to be false. So in this particular example, counterexample would be the room is dirty and he went to the pool. That would be one. Or he cleaned his room and no pool. A lot of times there could be potentially infinite counterexamples. And when you're looking for counterexamples, it's any statement that will prove it false. And so there's a lot of right answers when you're looking for counterexamples. You just have to find one. You don't have to necessarily find the same one as me or the same one as anybody else. As long as you find one that proves it false, then it's a good counterexample. Okay. We have converse. Converse flips the statement. So think about, you guys know Converse shoes, right? Chuck Taylors? Okay, you know how the Converse symbol is on the inside of the ankle, which is completely backwards from what it ought to be? If you think about, normally things go on the outside where you can see them, not on the inside of your ankle. And so that's how it helps me to remember the Converse flips things around because, you know, it's on the inside of the ankle. So Converse flips. So if you go to the pool, then you cleaned your room. No, it's not from the counterexample. It's just, it takes the statement and flips the beginning and the end. The hypothesis and the conclusion trade places. Right. Yeah. Yeah, if you got paid to wait, then you wouldn't work all week. So yeah, all it does is it turns them around. It just changes the order. Yeah, kind of. A biconditional happens when you take the original statement, if you cleaned your room, then you can go to the pool. And that's true. And you take the converse, if you go to the pool, then you cleaned your room. And that's true. If they're both true, you can put them together and make what's called a biconditional, which uses the phrase if and only if. You don't have to ever write that whole thing out in math. If you make two F's on an if, it means if and only if. And so you would write it as, you can go to the pool if and only if you cleaned your room. Oh, that stinks. That would be a counterexample, though. Yeah. That would make the statement false. Any counterexample makes it false. So if the pool was closed, the statement would be false that day. Yeah. Okay. So, but biconditionals can only happen if both ways are true, both the original and the flipped. And then you have an inverse, and inverses are negative, so they negate the statement. So if you don't clean your room, you can't go to the pool. Okay, so we have a regular statement, we have a converse which flips, we have an inverse which negates, so you just add don't or not or no. And then you have typo. Yes, everything gets saved. This is actually a contrapositive. There's a typo there. With a contrapositive, it both flips and negates. So we had flipped, if you go to the pool, then you cleaned your room. We had negated, which is if you don't clean your room, you don't go to the pool. And then you have both. If you didn't go to the pool, then you didn't clean your room. Okay, so conditional is the original if-then. Converse flips it around. Inverse makes it negative, and contrapositive does both. Okay, so conditional statements are really important in geometry. They're also, the one nice thing about learning proofs is that proofs are an argument, and once you know how to prove something mathematically and learned logic, because that's all it is it's logic. Once you know logic, you win arguments. So we have, if Marina does all her homework, then she will get an A in the class. This is conditional. We have Marina does all her homework, then she gets an A. The hypothesis is Marina does all of her homework, and the conclusion is she will get an A in the class. Okay, so when you have to identify hypothesis and conclusion, hypothesis comes after word if. Okay. Now, it can be written differently. It could be written, Marina will get an A in the class if she does all of her homework. The hypothesis is still that she does all of her homework because it always comes after the if. Yeah. So it could or could not be true. If she does all her homework but she fails all her tests, then she did not get an A in the class. That is a counterexample. Right? You could find like counterexamples are usually numerous. So you just have to you only ever have to find one scenario where she does all her homework but she doesn't get an A. Well, she didn't take the final. Yeah, I mean, there's a million of them. Exactly. Here's different forms of this conditional statement. We have the converse, which is flipped. So if Marina gets an A in the class, then she has done all her homework. We can find a counterexample for that too. Maybe she didn't do one assignment, but she still has an A. The inverse, if Marina does not do all of her homework, then she will not get an A in the class. The contrapositive, if Marina does not get an A, then she has not done all of her homework, so it's flipped and negated. Yeah.
Could it be flipped and false?
Yes. You can have a conditional statement that's true, but then the converse is false, which is why the biconditional only works if they're both true. Or you can have the other. You can have a conditional statement that's false, but then the converse is true. Let me think of one. I'm thinking. Here's the one. If Haley is a German Shepherd, then Haley is a dog. Or then she is a dog. Okay, that is true. My conditional statement is true. She's a German Shepherd. That makes her a dog. My converse, if Haley is a dog, then she is a German Shepherd. That's false. Yes. So if she's a dog, it doesn't mean she's a German Shepherd. She could be any of the other 1,000 different kinds of dogs out there. But if she's a German Shepherd, she's definitely a dog. So my conditional was true, but my converse was false. So you can have that happen. Does that make sense? Okay. Okay, so they may or may not be true. You have to decide that. Biconditional has to both be true. The previous example with Marina, with her grades, it can't be used because we could find counterexamples, right? She did all her homework, but she didn't get an A because she failed the test. Or she didn't do all her homework, but she still got an A because maybe she only didn't do one assignment, you know? So that can't be used. But we can use these. If you are a native Californian, then you were born in California. This is true, right? You're not a native California unless you were born there. If you were born in California, then you're a native Californian. Also true. So we can write the biconditional. You are a native Californian if and only if you were born in California. So you put them together, you take out the if and the then, and you stick an if and only if in the center. Does that make sense? But again, that can only work if both of those two are true. So the dog example I couldn't use because it wasn't true. Any questions on that? So, stating the hypothesis and conclusion, it's pretty simple. You take the part after the if and you underline it and you say, okay, that's the hypothesis. And then you take the part under the then and you say that's the conclusion. You guys won't be able to underline it, but you can write it off to this, like on your own paper. You can do hypothesis, and you can say triangle has two congruent sides. See, that's the beauty of geometry. We use symbols, and you don't have to write long sentences. And then the conclusion, it is isosceles. So you can do it that way. Converse flips. So if Sheila is a dog, then she is a terrier. Okay, this one was true. This one is false because maybe Sheila is a Rottweiler. Well, that would be a funny name for a Rottweiler. Yeah. I'd say more likely Sheila is a Chihuahua or a Poodle. Well, okay, maybe Sheila is a Rottweiler. Okay, if it is raining, then Charlie carries an umbrella. Inverse, so we flip, and then we negate. If it is not raining, then Charlie doesn't carry an umbrella. That's right. They're both false, actually, because what if it's raining but Charlie didn't bring an umbrella? Or here, what if it's not raining but Charlie carries an umbrella for shade? Okay, contrapositive does both, flip and negate. So if Lauren does not wear a dress, then she is not a girl. Well, none of this is true, because if Lauren is girl, that doesn't mean she wears a dress. Lots of girls don't wear dresses. You know, like lots of girls don't wear, and then if she's not wearing a dress, it doesn't mean she's not a girl. You see what I mean?
I